Here is a setup of 4 to 20 mA current loop based water level indicator. Looking into the block diagram, the first part would be the water level indicator itself, which acquires the data through this Bc557 transistors. Let's look at the dipping electrodes. So I have taken these jumper wires and tied it up this way to create electrodes. This is L1, L2, L3 and L4, and the bottom one is the reference, which is equal to VCC. This one would go right into the tank this way. Assume this to be a tank. Meanwhile, all these electrodes are pulled from the base of this Bc557 NPN transistor, and a reference VCC is let into the water. So through the base terminal, a small current would be picked up by this transistor, and in common emitter mode it would amplify, giving out high or low voltage, indicating with these LEDs. Next comes this R2r Ladder Network. Here the digitally acquired data, in the sense the LED high state or low state, is taken to this R2r ladder DAC, and these are the 4 inputs given to the R2r ladder. This is 2R, 4 2R resistors and 4 R resistors. Then the output is taken from here of the R2R ladder, and this would correspond to the analog voltage. This analog voltage is not specifically in 0 to 5 volt range, but to condition this to the transmitter, we need it in 0 to 5 volt range. So I have put up a simple non-inverting op amp which would take in any of this voltage and convert it into 0 to 5 volt range. Yeah, these are the power supply decoupling caps. Then, so having 0 to 5 volt perfect range, we then feed it to this current loop transmitter circuit. This is the OP8211 op amp. Since it is rail to rail, I have used it. Previously I tried it to the the UA741, but that was quite distortive. So this seems to be working fine, and this trim pot actually sets the current to which would follow through this loop. Will come there. Then next comes the Bc557 transistor. This op amp output drives the base of this Bc557, so that we can get the required current through the loop. Actually, this current to the loop comes from the collector of this transistor. So in this way we are virtually creating a current loop. Yeah, this is the collector terminal of this transistor, and that rightly comes through this loop. I have taken some 3 meters just for demonstration. As we know, the current won't drop along the wire. We can consider it to be of any length, maybe up to 3 miles probably. Yeah, so this current would be in the range of 0 to 20 milliampere, as the name of the circuit states. After that it loops back and goes to the ground. This is the receiver side of 4 to 20 milliampere current loop. Here comes the one end of the loop, and by putting a voltage drop resistor and measuring voltage across it, we would be able to interpret the state of these LEDs, in the sense the output of this R2r ladder ADC. So overall, what all these section does is simply it encodes this digital value of the water level into the current, and based on small variation in the current, you would be able to pick up that differential voltage, and again I'm feeding it to a OP8211, but this time it's a inverting op amp. just to drive these bar LEDs. Yeah, interpreted voltage would be in any range, like it may be from 0 to 0 to 2 volts, but we again need it in perfect 0 to 5 volt range just to drive these bar LEDs. So this inverting op amp converts that voltage to 0 to 5 volt range, and yeah, there is a small offset. Using these two resistive network, I'm giving a 2.5 volt offset to this amplifier. The output of this would again be 0 to 5 volt perfect, and that goes to these comparators. These are LM393 Ti part dual comparators. Since I readily did not have the driver for this bar LED, I just designed one by using 4 comparators. It would just compare whether the voltage is high or low regard to the reference, and then would drive this bar of LEDs. This is the drop resistor which will go here to the loop so as to interpret the voltage, but I have picked up and kept it outside now just to measure the current. So now let's check whether this 4 to 20 milliampere loop is really in that range. So I have tied up to the multimeter probe here those 2 points from the current loop, and then here currently we can see it is reading 17.5 milliampere. That is with nothing. I have not dipped it to the water at all. So now let me put this into the water and interpret if we really get the voltage. Yeah, this is level 1, 2, 3 and 4. There we go. And let me now see the current. It is 18.8 milliampere now. We'll see it together. I'm lifting this off. The current decreases. So overall, with the current difference of 17.5 milliampere to 18.7 milliampere, or now the 18.8 milliampere, all the values of these are encoded. So this rightly lies in the range of 0 to 20 milliampere. But of course we are not using the full range just because the conditioning circuit is not the standard one, and I'm using the power supply which is not of 24 volt. Yeah, regarding the power supply, which is the important part, I'm using this adapter which almost gives which gives 7 volt output, and all these sections are driven using the 7 volt. Then this is a buck converter which converts it to 5 volt, and only to drive this inverting op amp I'm using that 5 volt. Okay, that's because to drive this LED we need very precise 0 to 5 volt, and also I'm switching between these comparators, so otherwise it will be quite hassle and we won't get the exact reading in this bar. That's it for now, and this is the overall block diagram.